Hello, relativity friends. Yesterday, I made a video. I posted a video about basis vectors in Minkowski spacetime, and I look back at it, and I want to make something really obvious that I probably didn't because I tend to blow through things pretty quickly. This is just the old XY Cartesian, the plane, right? And on this plane, we can put a point, right? And from the origin to that point, we can put a line segment. We'll call it S, okay? Now, what equation would give the locus of this point? In other words, its equidistance from that point anywhere to the origin. Well, that's kind of obviously a circle, right? So no matter where I move that point, I get an equal distance from that, right? And we can measure that like this. We can say this squared equals the x component squared plus the y component squared. Just the old Pythagorean theorem, right? So if I actually put the values on here, so this is the x that squared, and this is that squared. And no matter where I move the angle, you see they always add up to 1. Okay? So we all know all that. Just wanted to put everybody on the same page. Okay, let's get rid of all of that. And now let's look at a different function. Okay? So if I put a hyperbola on here, like that, and I put a point on that hyperbola, that point there. Now, and I can put from that a line segment also, right? A line segment that goes to that point. Okay, so now how do we measure S? How do we measure this distance? You can't use the Pythagorean theorem. You have to use the equation of the hyperbola, which is that. Okay? So if I put those values on here, like this, so this is that squared, and this is that squared. No matter where I move that line, the segment, contrary to what your eye is telling you, you see S squared is the same number. It doesn't change. Even when I go negative, it doesn't change. Okay? So that's where that negative comes from. It comes from the fact that you are not in Euclidean space, you're in hyperbolic space. So, kind of the buzzword is you can't trust your eyes in space time, right? Because they will deceive you. So if I change that y axis, that's the wrong axis, by the way. What a dope. To this, now we have space time, okay? And now we're only interested in what is the, if an event occurs here and an event occurs here, when and what time did they occur? And the only thing you could agree on in space-time is this. It's called the space-time invariant, okay? Because each person at rest and the person traveling, will see this event and this event occur at a different distance. They'll see this event and that event occur at a different time. But when you use this space-time invariant equation, that's what they agree on. And the reason that negative is in there is because it's hyperbolic space. Okay, that's all I wanted to say. I just wasn't really sure that I made that clear yesterday because I blew right through that. All right, I'll see you later.